Thanks very much, everyone, for staying for my talk. I'd like to start by acknowledging the traditional owners of the lands on where we meet and the land and sea country where we do our research. First of all, my name's Peter. I'm a multidisciplinary research scientist from Southern Cross University. I'm relatively new into working with reefs. I come from a background of working in aquaculture and also ecotoxicology, so this is something that's going to be completely different. My talk today is the potential applications of remote sensing for mapping plumes in reef systems. I work as one of the team member of the RAP cooling and shading team. My presentation today will just give a brief overview of what we do, what we use now to measure our plumes, introduce two new instruments that we've added, and give a bit of sort of like preliminary data for our recent field work that we've just finished, and give some future directions and some potential opportunities for collaboration, data sharing amongst the different teams. The cooling and shading sub-program has been developing two technologies. We've got the seawater fogging technology and the Marine Cloud Brightening technology. They are designed for different spatial as well as temporal scales. The fog that we generate sits relatively low over the water. It's designed to shade the reefs directly, whereas the Marine Cloud Brightening, the MCB, is really designed to generate salt, which then will actually convect up into the marine cloud. It then actually perturbates the cloud and improves the reflectivity by increasing albedo. Okay, Southern Cross University has actually fitted out a Cessna 337 Skymaster, affectionately known as Bruce. It's been fitted with a range of scientific instruments that's really sort of operate in that cloud microphysics space, so something entirely different to what you're looking at on reefs. These instruments are designed to measure aerosol distributions and sizes. We also gather radiometric data. We look at things like cloud microphysics properties. We also collect general meteorological data like relative humidity, temperature, wind, speed, direction, etc., and also aircraft, and also using GPS through aircraft positioning. The instruments will actually collect samples of droplets and individual particles from about 10 nanometers up to about 2,500 nanometers. The main aim of this aircraft at the moment is that we want to actually characterise the MCB and fogging plumes, so looking at size and distribution of particles, the potential for light reflectivity. We're also monitoring those sort of interactions between the actual generated aerosol with the marine cloud to see whether we are actually perturbating these clouds, and also indeed to actually test whether they're actually susceptible to these little bits of salt crystals. Unfortunately, the one thing that's really missing from this whole kit is we don't really know the size of the plumes we generate and their 3D extent, and also indeed the actual changes of light field through the plumes. Hence, we've now added in a couple of remote sensing instruments. So we've added in, this one here is our HiSpecs V620 hyperspectral camera. It's actually a push broom style camera, if you understand. It actually collects data on 700 wave bands from about 400 nanometers through to about 2,500 nanometers. The visual range, sort of 400 to 700 thereabouts, is aimed, I guess, primarily at this stage, looking at reefs, whereas the shortwave infrared, which is sort of from the 800 to 2,500, is more useful when we look at the clouds and plumes and things. The bathymetric LiDAR, mainly designed to look at shallow water and coastal type environments, historically and most broadly used to generate three-dimensional models. We're going to be using this to look at the surface of the plume, so we can actually map and also in terms of the surfaces, also look at the surface of clouds. So we can actually assign individual heights to the individual pixels of the hyperspectral camera, because there's a lot of cloud microphysical properties that rely on an exact knowledge of altitude. So that'll help us drive that knowledge. The addition of these instruments has improved or will improve our capabilities. You're all aware that there's a lot of technology with drones. They've certainly improved the access to information, but they're relatively limited in their range, and they are impacted by weather fairly significantly when you then compare it also to satellite. The resolution of most satellite products at the moment over the ocean are about 1 kilometre square. We're operating in a range of, resolution down to about 20 centimetres square. So as I said, LiDARs are generally designing three-dimensional structures of reefs and land masses. Here we've got a little DEM we've created of a charity reef at about a 0.5 metre by 0.5 metre square. We can get returns from the LiDAR down to about 15, 20 metres, really dependent on water clarity. Using the LiDAR, we can actually make estimations on the albedo of individual plumes using full waveform analysis, something similar to what we use in a celiometer. We can estimate the amount of shading we can generate through the plume at various sections through the plume. We also examine individual edge effects for light fields modifications. And of course, we can measure plume's extent, most useful for the seawater fogging. Now, in the interest of time, I'll only run through looking at the plume. In our recent field campaign, we were on the Whitsundays. Weather wasn't the best. We didn't manage to actually LiDAR the actual fogging plume, but we did for the MCB plume. So what I'm going to show you is some more, proof of concept data, just to show what we can do. So here is what we found with the MCB plume. This is a single flight, 500 feet, 100 knots, so for the uninitiated, about 150 metres at about 180 feet, about 185 kilometres an hour. Single pass right over the top of the boat. We're able to get this. And as you can see, we've got about a 300 metre plume, and we've got a vertical development of about 20 metres. Now, this is not its primary use case, but this is fairly encouraging. Similarly, when we look at the top-down view, we can see there's actual, some form of horizontal development. We've got about a 30-metre development here. So while this is only preliminary and it's not its actual primary use, it shows that we are able to use this sort of information to measure volume and the lateral and vertical development of these plumes. We do expect to get much better resolution from the fogging plumes, and that's mainly a function of the size of the droplets. As you can see, the fogging plumes are much larger in droplet size. This is actually where the LiDAR laser sits in terms of its wavelength, so we're expecting to get a lot better returns, simply based on the overlap of that size distribution of the individual particles. For comparison, the figure there on the side is of one of our fogging plumes. It's about 600 metres long and about 100 metres wide. So it's significantly bigger than your Marine Cloud Brightening plumes. When we look at the hyperspectral data, this is a small section of Heron Reef that we captured about 2 weeks ago. It's sort of traditionally been used to focus on terrestrial and shallow water environments for change analysis and materials classification, etc. However, these analyses rely on sort of extracting individual spectra from regions of interest and then generating interesting products that show what you want. But the high dimensionality of this hyperspectral data will allow the detection of regions of image that are maskable or of interest so that we can actually focus on those. When we apply this to our plumes, you can see there's the opportunity that we can actually find a lot more information, and we can potentially also see any interactions with what's going on with the light fields on the reefs that are actually underneath the plumes. So what are we looking for in the future? Well, we're already actively working on trying to use the LiDAR data to build up some fine-scale modelling, and we can also look at the reef analysis to support habitats for restoration. We can use the combined data to work on trying to identify those suitable habitats, whether it's less rubble, more rubble, whatever's available. And we're also designing a machine learning algorithm to help us actually do the early detection of bleaching. So in summary, we are able to use these instruments to find plumes, but that's just the tip of the iceberg of the information that we can actually get out of these. Listening to a lot of the talks here over the last day and a half, I see a lot of pain points that potentially could use this sort of data. So if it's of any use, just get in touch. We're more than happy to help. So thanks very much.
Any questions? How long do you find those fog plumes last?
The fog plumes are very dependent on wind, as you'd expect. You probably, from when the machines are turned off, 15, 20 minutes. It's very much like having a low-level cloud for the fog. For the MCB stuff, it's really not about the plume. It's all about the salt. Yeah.
Thanks, Peter. With the detection of very small particles, can plumes and small particles in the water be tracked, or is it only those tiny particles in the air?
Not something we've looked at, but owing to the fact that the resolution is sort of a square this size, if it's got some light property that we could look at in the spectra, then potentially, because obviously they can track algae from space. So if it's something that we can get a spectral return from, then potentially there is opportunity.
Sherry?
I'm just going to add to that question, which is the answer is yes, you can detect plastics using this kind of technology, so which is what I'm interested in. But my actual question was, what is the salt? Is it just sodium chloride? Is it a mixture of salts?
It's just seawater.
It's just seawater.
Just
okay,
seawater. All we do is, and there'll be more about this in some of the presentations tomorrow. But literally, they just need to pump the seawater out. It gets filtered, and then it gets sprayed out at under high pressure.
So I'm particularly interested in that because there's a chemical known as DMSP, which is produced by corals and then gets converted to DMS. And it's a salt that can be readily dissolved in seawater and then sprayed, and it's linked with cloud or sulfur cycling. And I think that could be a particularly interesting area to consider.
It's something we're already looking at in terms of the atmospheric stuff, yes.
Perfect.
All right, we'll just take one more question from our online audience. For implementation of fog, the dispersion would primarily rely upon prevailing wind conditions. How do you expect the coverage to change for stationary sources?
Yes, the wind does have a significant impact on its dispersion. The envisaged scenario, I guess if that's the right word, is that you'd actually have multiple stations around a high-value reef, and it is really dependent on the wind, so we need to have those low, almost sort of like doldrum-like conditions for it to be effective, which thankfully do occur over the reef during summer. And the idea is by having multiple points is that we can try and alleviate the effect of that wind drift, you know, at least minimise it anyway.
Okay, can you join me in thanking Peter, please?